You batch a concrete mix with a specified strength of 35 MPa. You cast the test cylinders with care. But when the lab results come back, the strength is only 28 MPa. What went wrong? The mix design was perfect. This frustrating scenario happens all too often, and the root cause is almost always a failure to control one of the critical factors that govern concrete strength. Understanding these factors isn't just academic. It's the difference between a structure that stands for a century and one that requires expensive repairs in a few years. In this video, we're going to move beyond the textbook and dive into the practical, real-world factors that you, as a site engineer or contractor, can control to ensure you hit your target strength every single time. We'll start with the most important one, the factor that overrides all others. The single most important factor controlling the strength and durability of concrete is the water-cement ratio. This is not just a guideline. It's a scientific law established by Duff Abrams in 1918. The water-cement ratio is the ratio of the weight of water to the weight of cement in a concrete mix. Here's the fundamental principle. For a given set of materials and conditions, the strength of concrete is inversely proportional to the water-cement ratio. This means that as the water content goes up, the strength goes down, and vice versa. Why is this? Cement hydration requires only a specific amount of water, chemically bound, which is roughly about 0.23 to 0.25 by weight. Any extra water that isn't used in hydration remains in the concrete as capillary pores. These pores are voids. When you load the concrete, these voids are the points where cracks start and propagate. So, a higher water-cement ratio means a more porous, weaker concrete matrix. A pro tip from concrete technologists: reducing the W/C ratio from 0.5 to 0.4 can increase the 28-day strength by as much as 50%. However, there's a catch: a lower with C ratio also makes the concrete less workable. This is where the next factor comes in, and where many site crews make a catastrophic mistake by adding unplanned water on site. The second factor is the degree of compaction. Concrete, as placed, is full of air bubbles, typically 5% to 20% entrapped air. The goal of compaction, whether by vibration or rotting, is to expel this entrapped air to create a dense, homogeneous mass. For every 1% of entrapped air you leave the concrete, you can lose about 5% of your compressive strength. Think about that. If you have 5% voids due to poor compaction, you've potentially lost a quarter of your design strength. The concrete will be honeycombed, porous, and vulnerable to water and chemical ingress. A common and devastating site error is adding water to make concrete more workable and easier to place, instead of using proper vibration. You might improve workability, but you've severely increased the water-cement ratio, which damages the strength far more than the improved compaction can help. The correct approach is to design a workable mix with the right with C ratio, and then use mechanical vibration to achieve full compaction without segregating the materials. The sound of good vibration is a low rumble as the air bubbles rise to the surface, and the concrete becomes fluid and glistening. Now, let's talk about the raw materials, starting with cement. The type, brand, and even the batch of cement can influence the rate of strength gain and the ultimate strength. Different types of cement are manufactured for different purposes. Ordinary Portland cement gains strength at a standard rate. Rapid hardening cement is ground finer or has a different chemical composition to achieve high early strength. Blended cements like Portland Pozzolana cement have slower early strength gain but excellent long-term strength and durability. The key is to always use the cement type specified in the mix design. Furthermore, the age of the cement matters. Cement that has been stored for months, especially in humid conditions, can absorb moisture and prehydrate, losing its reactivity. This is why you must always check the manufacturing date on cement bags and perform regular tests to confirm its strength. The aggregates you use play a surprisingly significant role in the final concrete strength. While the cement paste is the glue, the aggregates are the bulk of the volume. Their properties matter immensely. First, the strength of the aggregate particles themselves must be higher than the concrete strength you're trying to achieve. You can't make 50 MPa concrete with soft, weathered gravel that crushes at 30 MPa. This is why we perform tests like the aggregate crushing value and the Los Angeles abrasion test. Second, the surface texture matters. Rough, angular crushed stone provides a better mechanical bond with the cement paste compared to smooth, rounded river gravel. This superior bond can lead to higher strength, particularly in flexural and tensile strength. Third, the gradation we discussed in the previous video is critical. A well-graded aggregate pack with minimal voids requires less cement paste to fill the gaps, allowing you to use a lower with C ratio for the same workability, which directly boosts strength. One of the most underappreciated factors is the curing process. Curing is the process of maintaining satisfactory moisture and temperature in concrete for a sufficient period to allow the hydration reaction to continue. If concrete is allowed to dry out, hydration stops and strength development ceases. The surface, being the most vulnerable to drying, becomes weak, dusty, and prone to cracking. Properly cured concrete can be more than 50% stronger than identical, uncured concrete. The duration of curing is also critical. While concrete gains most of its strength in the first 28 days, hydration continues for months and even years. Stopping curing after just 3 or 4 days is a common mistake that sacrifices significant long-term strength and durability. For high-performance concrete, wet curing for at least 7 days is a minimum, and for concrete with supplementary cementitious materials like fly ash or slag, longer curing is essential as they hydrate more slowly. Finally, we have the temperature and age factors. Concrete strength is a function of time and temperature, a concept known as the maturity of concrete. The hydration reaction accelerates in warm weather and slows down in cold weather. This means a concrete slab poured in the summer will gain strength much faster than the same mix poured in the winter. However, there are limits. If the temperature is too high during pouring above 35 degrees Celsius, the reaction can happen too quickly, leading to thermal cracking and a less dense microstructure, which can result in lower ultimate strength. Conversely, if the temperature drops below freezing, the water in the mix can freeze and expand, disrupting the concrete matrix before it has gained any strength, causing permanent damage. Regarding age, concrete never truly stops gaining strength, but the rate decreases dramatically after 28 days. The 28-day strength is simply a standard benchmark. Understanding the maturity concept allows you to make smarter decisions about when to remove formwork or when to post tension slabs based on actual in-place strength rather than just a calendar date. In conclusion, concrete strength is not a single input, single output game. It's a complex interplay of the water-cement ratio, the quality and compaction of the materials, and the environmental conditions during curing. You cannot compensate for a high water-cement ratio with better cement, and you cannot compensate for poor compaction with longer curing. Each factor is a critical link in a chain. To guarantee strength, you must control all of them. By mastering these factors, you move from being someone who just pours concrete to someone who engineers it. Now I want to hear from you. Which of these factors has been the most challenging to control on your projects? Is it maintaining a low with C ratio with a site crew, or ensuring proper curing in hot and windy conditions? Let me know in the comments below. If this deep dive has helped you understand the levers of concrete strength, please hit the like button and subscribe for more content that builds your engineering expertise.